What is the relationship between decomposition calculations and standard algorithms? Let's see. First, let's agree on what each is called, because we refer to a type of calculation as decomposition, which in the literature, let's say, more specifically for this area, are called column calculations. We base ourselves a lot on Dutch literature, which we use as a reference for many of the capsules that we have here. And in all of these references is the Freudenthal Institute, which we base ourselves on, and in their material, what we call decomposition calculations are called column calculations, yeah? And the traditional or standard algorithms, the two words are often used as a synonym. What we are referring to are the algorithms that adults learned when we went to school. Some algorithms which have some specific characteristics that we will analyze, which are a little bit different to the column algorithms or decomposition algorithms that we've spoken about. The first thing that we must make clear is that whether it is called traditional or standard is relative, because it depends greatly upon the historical moment and place. That is, the way in which subtraction was traditionally carried out in Spain, for example, may be different than what I learned about subtracting, doing it the way I learned in Uruguay. That is to say, it isn't exactly the same. Traditional is only traditional in a small place. It is standard in the sense of standards shared by a community, but another community may have another. It is not an absolute term, let's say. It is not that everyone subtracts the same, and less so that everyone divides the same. That is much better known. The aesthetics of standard division in other European countries is very different from what we have, and the same goes for additive operations. It may be that aesthetically they look the same, but they do not have to be exactly the same, and we will analyze it later. The truth is that the algorithms, those that we call standard or traditional, have centuries of history. Let's say that they are closely related to the introduction of Hindu-Arabic figures, which we use, and therefore, traditional algorithms, we do not want to banish them because we believe they have a social and historical value, which is also an obligation of the school to transmit. What happens is that we argue that this historical value, it represents us, that it is the only algorithm that we have to teach, or at least it is the first, right? So that is why we have introduced algorithms by decomposition, vertical schemes that rely much more on decomposition, because we believe that they are a good way to develop mathematical knowledge for students to learn to add and subtract, and that they will also allow us to try at some point, let's say, the standard algorithms, and it may even happen that they assume them as their own, let's say, in the case of some students. Let's see, what characteristics differentiate these two types? The fundamental characteristic, which is also shared by other didactic proposals, not only the one we have in the numbers laboratory, is the fact that algorithms by decomposition do not work with digits but with numbers, right? I'll use an example to make it very clear. When we add 43 plus 25 with a traditional algorithm, we add 3 plus 5, 8, 4 plus 2, 6, and we're left with 68, but we say 4 plus 2. When we use the decomposition algorithm to do this calculation, we separate the 43 as 40 plus 3, the 25 as 20 plus 5, and so we add 3 plus 5, 8, but 40 plus 20, 60. We never lose sight of the fact that this is not 4, but rather 40, that this is not a 2, but instead it is a 20. We always work with quantity, yes, and not simply with the figure, let's say. In addition to the fact that this is more natural, let's say, much more linked to manipulative material, an advantage that I would like to highlight at this time is that working with quantities and not with figures gives us the opportunity to always estimate the answer. When I say that I am adding 40 plus 20, and that gives me 60, I already know that the answer will be close to 60. You can get to 70, but you can never give me 700 or 300, nor can you give me 20. This allows me to accompany the exact calculation with a calculation by estimation, and it allows me to develop in the students an attitude of self-checking of the results, of being very critical of the results that are obtained, which is very good. Many times, when we correct students' work, we ask ourselves, but how could they have come up with this crazy answer? What may have happened is that we never reflected on the approximate calculation that must always accompany the exact calculation. Not only the exact written calculation, even when we use a calculator, it is convenient to keep in mind what dimension the number it gives us must have, because that way we detect errors and we can correct them. Therefore, the first difference that we have established between the two types of algorithms, traditional and decomposition, is the fact that one works with digits and the other with quantities. A second difference that we can name is the fact that traditional algorithms are very rigid. I always have to start from the right and go taking things and go to the left. When I work with algorithms by decomposition with a sum, I can start with the tens or I can start with the units, because what I am doing, as always, I keep the quantity, then I can make the readjustments before or after, right? Therefore, this freedom that column algorithms or decomposition algorithms give me is very good for us. And furthermore, I also reiterate the relationship it has with the manipulative material. If they give me a number of euros here and another number of euros here, and they say, how many euros do I have in total? I usually add bills first and then coins. Therefore, it makes perfect sense to start from the left and not from the right. And let's say traditional algorithms, well, they don't see that so clearly, because there is an order to do things in, which doesn't allow us to start from the left. Finally, the last differentiating feature that I would like to mention here is the fact that traditional algorithms are very rigid. Traditional algorithms tell us that we have to do everything using the least amount of paper possible, right? They do not allow me to write down the intermediate steps. I have to go and follow the steps indicated by the algorithm and arrive at the result. Decomposition algorithms allow us to have students at different degrees of abstraction. In other words, some write a lot, but they understand what they do, and others have already been able to do all that, see that they can write less, make it more efficient, and gradually approach a compressed version. We must bear in mind that at the time traditional algorithms were developed, paper and ink were scarce goods, but this is not our case. Here, our fundamental objective is that the student understands what they do and that they arrive at the correct result. If you need to make a little green box where you place intermediate results and then arrive at the result, there is no problem. This does not mean that we do not invite the students to compress, because later what we need is this addition or subtraction algorithm, this being a step within a multiplication and division algorithm, and if we make the addition and subtraction algorithm too long, then imagine how long multiplication and division would be. Therefore, we have to have the two things clear, correct? The benefits of one and of the other. But we have highlighted three differences which seem to us to be fundamental between one type of algorithm and the other. Why, when working with calculations by decomposition, do we ask students to shorten their processes? It's a key theme in the topics of this capsule. The most important thing is to find the balance point and have some points, let's say, that we are sure about. A first point is that the important thing for students to learn is how to add and subtract, and not how to master algorithms. The important thing is that when writing reports for children's families, I don't confuse comments like "they find addition hard" with "they find addition algorithms hard." That's a critical element. So, if a student knows how to add, but let's say their process is very long, we ask them to compress it, but we can't say that this student does not know how to add or does not know how to subtract. After having differentiated what the concept is from what a process associated with the concept is, we want to make it very clear that this is a long learning process. We start by adding and subtracting by manipulating base 10 blocks. Then we move on to representing the base 10 blocks and representing what we were doing manipulatively by representing it on paper. There are students who, while others are already representing it on paper, still need materials. And that's no problem. We let them do that. But as we move forward, we also need them to leave the materials behind and move on to representation. For those who have already mastered how additions and subtractions are done from representing it on base 10 blocks, we encourage them to move on to use strategies that mirror using blocks, but without the need to explain them, as in to draw them. And over time, they develop more ways of expressing this symbolic representation until we reach our endpoint, our goal, but not the goal in the sense of an objective, but in the final sense of the journey, which is the standard algorithm because it is the algorithm that is characterized as being the most compressed of all, the one that saves the most, not always time, but the most space. Not always time because if a child finds it difficult, they will take longer using the standard algorithm than decomposition because they understand it and can do it. So the idea is always to encourage the children to move on to the next level of abstract thinking, not to skip any stage or to ask them to take that leap too early. We have to see this as a long-distance race, let's say, not as a 100-meter race. The idea is to accompany the students on a long journey and encourage them to continue, but to always return to the previous step if we see that they are systematically making mistakes in additions or subtractions at one stage, then encourage them to go to the previous stage where they feel safer, and from there take the step forward. So the basic idea here is balance. If we want to approach standard algorithms, why do we start by doing decomposition calculations, which are represented very differently? An initial idea that we have to highlight is that studies that show a premature introduction to a process as significant as the standard algorithm, significant because it can solve all cases and because it takes up very little space, regardless of whether it's clear, that is, that many of the children we teach it to don't understand why it works. They just need to think about the subtraction algorithm. Many students don't understand why doing those steps gets to the result. But the basic idea is that an algorithm, a significant process, leads to cognitive passivity. That means that by the time we teach it, by having a tool that solves all problems, students can begin to use it regardless of whether it is the most appropriate in that particular case. Not only does that happen with addition and subtraction or with multiplication and division, it happens with all the mathematical processes we teach in primary and secondary education. school teachers and math teachers always have to be very clear about not rushing to provide answers to problems students haven't had yet. If students don't need to make a process shorter, let's not offer the summarized version. Let's let them be the ones who discover how to summarize and compress it. So, I take into account that if I teach it very early, I will not be able to develop other strategies because the students will not absorb the strategy and will only use the algorithm. So we postpone teaching this algorithm as much as possible. It is not a waste of time working on the decomposition strategy. We have to be very clear that it enriches learning because while I am working with that strategy, I develop my numerical sense. I can work through many addition strategies that students can then choose from. I use this one right now, and in this one, I use the standard algorithm. But I need to spend that time teaching them and for students to feel comfortable with those other strategies. And I also have to be very clear, working on the decomposition strategies allows me to approach the traditional algorithms in a transparent way. That is, I can teach the traditional algorithms, and I can do it in a way that students will be able to understand why it works, why such a sophisticated tool solves the situations they are dealing with, like addition or subtraction. So, that's why we spend a long time teaching without talking about algorithms, simply just the decomposition and jumping strategies. And then at the end of this slow and gradual process, that's when we talk about the algorithm. Also, something else that is happening is that, of course, all math teaching is becoming much more about competence and less about mechanics, as it was in the past. And that is not restricted to a specific type of activity. Even in activities that we associate more with mechanics, such as the development of arithmetic processes, learning competence is important, and so is reasoning, representation, and communication. And in our process to develop decomposition strategies to get to algorithms, we believe that we bring into play all these mathematical processes that are so important and that inspire our curriculum. Our students are motivated to use them on a daily basis in the classroom. One last aspect that I would like to mention is the fact that even if we are already teaching, we have already come to the end. We are working with standard algorithms and, for example, it may be that we are already working in middle or upper primary. Nothing prevents us, when using a standard algorithm, from accompanying it with a discussion on quantities. This aspect of the decomposition algorithms can be transferred to standard algorithms. If I am calculating 43 plus 25, nothing prevents me from doing 3 plus 5, 8, 40 plus 20, 60. There's no need to stop naming the quantities, the digits. And therefore, I would also keep that knowledge of the huge benefit that standard algorithms have. I would not want to lose it just because I'm working with traditional algorithms.